Hello and welcome. In today's exercise I will introduce you rotational matrices. Rotation matrix. The rotation matrix is a very convenient tool to describe a rotation in 2 or in 3 dimensions, and we will need this to derive the forces acting in a non-inertial rotating coordinate system. And before we go into depth with these, in another exercise, we will, in today's exercise, derive these rotational matrices. Some of you might have seen them before, so maybe it's not much fun to follow this exercise, but if you haven't seen them, I very much suggest that you try to follow this exercise with pen and paper. And what it is about is about a rotation and is about a matrix. And we will today have a look, the first time, a look on a matrix in this course. So what is it about? We want to describe a rotation, and we describe the rotation in a coordinate system. Let me delete this one first. Again, try to do a bit nicer. So this is the coordinate system, x and y, and this is y, and then we have a rotated coordinate system which is rotated under some angle, and this has not the coordinate system x but x prime. That is commonly used in physics. And this is y prime, and the angle here between the two is still 90 degrees, but we have a rotation angle which we call theta, and these angles have also a direction. They're counterclockwise, and counterclockwise are these angles positive. That means a positive value is against the orientation of a clock. Now, what we want to have, or want to derive, is given a coordinate in the rotated coordinate system, x prime, y prime, let's say x prime and y prime, and the rotation, what is the position of it in the unrotated coordinate system? Or the same one, what is the position? This is another function, g, x prime, y prime, and theta. What is this? And these two equations, we will have a look at it. I will derive the first one, and maybe that is something you can do yourself. And we will derive the first equation, relating the position, which we call here x prime, y prime, in the rotated coordinate system. Okay. And what is it in the unrotated coordinate system? Let me get the black pen here. So this is y, this is x, this is y prime, and this is x prime. Okay. To derive this one, actually it's rather simple, straightforward. We just need two more variables. This one I call delta x, and this one I call delta x prime. And then we can write that delta x, again, delta x is this distance, and delta x prime is this distance. So we can then write delta x is the whole length here, which is x prime, minus delta x prime. Now, delta x prime, what is this length? We can see that the triangles are similar. So this triangle here, the angle theta, ends up here 2. So here we have also an angle theta. This is a 90-degree angle. So this angle and this angle are the same. Therefore, we can write tangents of theta in this one is this one delta x prime divided this length, and this length is x prime, y prime, sorry. So we can write this one as x prime minus, and delta x prime is then y prime times tangents of theta. Now let me multiply the whole equation here, this equation, with a cosine of theta. You will see immediately why I do this. So this equation will be then delta x times cosine, and x prime times cosine of theta minus, and tangents of theta is sine divided the cosine, so it's then y prime sine of theta. Why do I have this one, or why is this so important? Let's look in this triangle here, and there we can say the cosine of theta is this length, divided the hypotenusis, so it's delta x, so it's x divided delta x. Therefore, delta x times cosine theta is nothing else as x. X is x prime cosine of theta minus y prime sine of theta. So therefore, we have now an equation where on the left side is written x on the right side, and left side on the right side is the function, which is the function of x prime, y prime, and theta. X prime, y prime, and then theta. Now you can do the same and derive an equation for y, which is not that difficult. And I just give you this result for this one is x prime times sine of theta plus y prime of cosine of theta. You see already here the shape of these equations. And this equation can be abbreviated using a matrix multiplication. Just to motivate it, we can write x and y as a vector, that is the position, this position, not forward this one, and x and y is cosine of theta minus sine of theta. Here we write sine of theta, and this is cosine of theta, and we multiply this whole thing with x prime and y prime. So this is a matrix multiplication with a vector. So you apply this matrix on this vector, and if you multiply it, you have cosine theta x prime plus minus sine theta y prime. So this is the first line, and this is the first component of this vector. So it is an abbreviation, and we can abbreviate it even further. We can say this one is actually a position vector. We give the name r. R is commonly used for position vectors. R is the position vector in the unrotated coordinate system, and this one is a matrix, and we call this as a rotation matrix. Therefore, we call it theta r, and it's a function of theta. And the right side is a vector, and we write it as a prime vector. Now, to distinguish between matrices and scalar quantities and vectors, we use different ways of writing it. If you find a mathematical text, it's commonly used a bold-faced or a calligraphic character. Here I use the following distinction. I put 2 lines below a letter, and this says that this quantity here is actually a matrix and not a scalar. So in short form, this is the rotation operation. R of theta is the rotation matrix, which transforms, that is a mathematical language, transforms a position vector in a rotated coordinate system into a position vector of the unrotated coordinate system. Or in other words, consider you have something which is spinning, yes, and you want to know what is this position which is spinning in a non-spinning coordinate system. And this I want to show you with MATLAB. We will use this matrix, we put it into a MATLAB program, and we will spin a vector x prime, y prime, and see that the position, and plot this position in a fixed coordinate system.